días miércoles de cada semana. También yo puedo sacar los desechos plásticos. Perdón, entonces los plásticos son el día miércoles y los otros días son los plásticos incombustibles. Este estilo eh, es muy popular en Japón. Así es que antes de 2021 también se categorizaron en otros tipos de desechos reciclables.
Necesitamos agua, gente, para los plásticos reciclados. Se me olvidó tener agua. Los plásticos reciclados son transportados por una empresa privada que recoge y la transporta. Esta foto muestra la última máquina que recicla. Esta máquina puede separar el residuo plástico en PP, PE y PS. Aparte de eso, esta máquina puede separar los residuos según color y forma, usando identificación mediante cámaras e imágenes. Los residuos plásticos son reciclados con distintas tecnologías en Japón. El reciclaje más popular es el reciclaje químico y mediante investigación. Este es un caso interesante en Japón. La empresa de bebidas Coca-Cola ha empezado a recoger las botellas PET y las recicla en forma horizontal mediante motores. Eso en forma horizontal, un sistema de reciclaje horizontal. Para algunos reciclajes, los residuos plásticos, para algunos recicladores mezclados que no son apropiados para los materiales químicos. Esto está mezclado con papel comprimido. Oye, ¿cuál de todo esto anda como fucking nightmare? Estos son algunos sistemas de reciclaje. Están comprimidos y esta compresión se llama RPF, con papel y combustible de plásticos. Tienen el mismo valor y también el costo de producción es más bajo. El sistema de RPF es muy popular en Japón. Me gustaría avanzar con el tema de la estrategia nacional del residuo plástico en Japón. Esta muestra la estrategia nacional para el manejo de residuos plásticos del gobierno japonés. Formuló la estrategia de circulación de recursos para los plásticos. Está basado en tres hitos, 3R, que es reducir, reutilizar, reciclar y renovables. El número 4, el 100% de los plásticos utilizados que sean reutilizados y reciclados en el 2035. Es un hito muy desafiante. En Japón, los recursos nacionales como recursos reciclados es muy importante como acción en Japón. El responsable para este proyecto, el ministerio, quizás el profesor Oscar puede explicar un poco esta parte, el, el acta de reciclaje de plásticos. Estas son estrategias nacionales y específicas. Un punto importante a considerar: es importante reducir el uso de plásticos de un solo uso, y para la tecnología, la corrección del sistema de separación de plásticos y la acción de cero emisiones para el océano es muy importante. Y de acuerdo a la autoridad local, es que tienen que separar los plásticos de otros residuos. ¿Qué tipo de productos plásticos están en esta categoría? Y la segunda encuesta es para entender cuánto contienen los residuos plásticos. Esto demuestra la forma de reciclar plásticos en cada bolsa. Ahí tenemos distintos productos plásticos y se pesa, se mide su peso. Esta foto muestra distintos productos plásticos. Bandejas.
Containers and wrapping film, something like that. And this graph shows the results, the composition of plastic products collected from the recyclable plastic waste. PET bottles and food tray and wrapping film accounted for large composition. And to my surprise, 15.9% of non-plastic waste was contained in the plastic waste categories. So I picked up some food waste such as cabbage and cucumber in the plastic waste. It was very surprised. And this slide shows the second composition survey view. We collected the recyclable plastic waste in the burnable waste. So 2% of the recyclable plastic waste was contained in the burnable waste. I think these survey results suggested the awareness activity of sorting waste for citizens is more needed. And we fed back these results to our governmental headquarters for supporting to make prefecture policy and awareness activities. So our headquarters Department of Environment in Saitama Prefecture has established a platform for promotion of plastic resource recycling and utilization in Saitama in 2021. In this platform, seminars and workshops were held to several stakeholders, such as waste treatment service companies and local authorities and some consumer organizations. This platform has a and our survey results also shared at this platform. And this platform is still active today in order to explore the establishment for sustainable plastic resource utilization models. So connecting to the companies B2B system or B2 government, business to government, making a network and something like that. Here is my conclusion. In Japan, central and local government is making efforts the resource circulation strategies for plastic waste. And these activities are still ongoing. And it is revealed the awareness for citizens is important for plastic waste recycles. And I believe the market expansion of recycled plastic materials will be the challenge for the future. And to the end, the big collaboration of industry, government, academia will be more important. So I look forward to the continue our cooperation. Thank you for your attention.
Muchas gracias por la interesante presentación. En este caso tenemos buenas noticias porque efectivamente gracias a los esfuerzos que está haciendo el gobierno, en este caso de Japón, y que puede ser replicado, ¿cierto?, también en otros gobiernos de otras partes del mundo, podríamos tener efectivamente
have a better recycling, and therefore a lesser amount of microplastics in the environment. So in fact, this is good news, which you have shown us today in this interesting presentation. Gracias por tu presentación, Yugo, y esperamos con interés la próxima presentación.
nuestro próximo presentador. Ahí. Es el doctor Kotaro Murata, también del
from the Center for Environmental Science in Saitama, and he's going to deliver a presentation about a very interesting issue related to particles with the about the concentration of particles that can be forming ice particles in the nucleation formation of clouds, in this case with measuring in Fuji Mount. Thank you very much for your presentations. So, and now I'll leave the floor to you. Gracias por la presentación. Estoy muy honrado de tener la oportunidad de venir a Valparaíso y hablarles hoy en este fantástico auditorio. Estoy ahora llevando a cabo observaciones en la cumbre del monte Fuji.
And the bioaerosols. Today, I would like to present the results of these observations up to this point. My collaborators are these three individuals, each of whom has been conducting research in atmospheric chemistry or atmospheric electricity at Mount Fuji for over 10 years. The person in the middle is a Professor Okochi studying atmospheric microplastics, who recently published a fascinating report about atmospheric microplastics observed at the top of Mount Fuji. I'll mention it later. Then first, I will explain what ice nucleating particles are. Ice nucleating particles, often referred to as INPs, are aerosol particles that act as nuclei when water undergoes a phase to ice in the atmosphere, promoting the formation of ice. The presence of INPs allows purer water to freeze at temperature higher than its normal freezing point. Common substances that function as INPs include mineral particles, and recent research has shown that biological particles such as bioaerosols are also significant. Particularly, a type of Pseudomonas, as shown here, is known to act very efficiently as ice nuclei and has even applied in artificial snow making. Now I will explain how INP is related to cloud formation using convective clouds that produce rain as an example. First, clouds are composed of water droplets and ice, but they cannot form with just moisture alone. Aerosol, known as cloud condensation nuclei, are essential for the formation of water droplets. Water-soluble aerosols such as sulfate and sea salt contribute to this process. The water droplets that form in this way do not freeze immediately at sub-zero temperature in the upper atmosphere. They actually exist as supercooled droplets at temperature down to about minus 38 degrees. However, when we observe clouds, we can find ice crystals are present at the temperature above minus 38 degrees. This indicates that the presence of INP contributes to the freezing of water in the range from 0 degree to minus 38 degree. Okay. The formation of ice in the upper atmosphere is crucial for the process of rain formation. When ice forms in cloud where water and water vapor coexist, the ice has lower saturation vapor pressure than water, causing it to draw water vapor from the surrounding droplets, allowing the ice to grow. The growing ice eventually falls, creating a chain reaction that leads to the formation of snow or rain. This process is referred to as cold rain. It is said that 80% of precipitation, 80% of precipitation in the mid-latitudes occurred through this process, highlighting that the formation of ice in the upper atmosphere, specifically the presence of INP, is key to rain formation. Then what I am currently working on is conducting observation of INPs at the summit of Mount Fuji, the highest point in Japan, in order to understand the reality of INPs in the upper atmosphere. The advantages of conducting observation at the summit of Mount Fuji is that its conical shape and isolated peak make it less susceptible to the complex wind effects caused by terrain compared to other mountain sites in a mountain range. This allows for relatively straightforward interpretation of the results. And observations are conducted at the facility known as the Mount Fuji Research Station. As shown in this photo, it is located on the southwestern edge of the crater at the summit of Mount Fuji. Now let me provide a brief history of the Mount Fuji Research Station. Meteorological observations were conducted by the Japan Meteorological Agency at this station from 1932 until 2004. After that, the station became unmanned and was destined for demolition. In response, a group of atmospheric chemistry researchers stepped forward to establish a non-profit organization to take over the operation of the facility, making it possible for research use under a rather ambiguous agreement. Since then, this non-profit organization has made immense efforts to raise funds through grants and donations, enabling observations to continue each year up to 2024. And by the way, I became one of the director of this organization starting this year. If you ever wish to conduct observation at the top of Mount Fuji, feel free to reach out to me. Then I will coordinate with the NPO. Okay, now to return to the topic. The observation being conducted at the summit involve collecting airborne particles on filter to measure INPs. The particles collected on the filter are suspended in molecular water and INPs are measured using a method known as the droplet freezing method. From the suspension of particles, 100 droplets of water were created on a copper plate of the cooling plate, and these droplets are then cooled down. If the droplets contain INPs, they will freeze at higher temperature than pure milky water. By measuring the proportion of frozen droplet at various temperatures, we can calculate the concentration of INPs. In this study, the freezing rate is observed in increments of 0.5 degrees. The example shown in the lower right illustrates the measurement of ice nucleating particle concentration. The horizontal axis represents the activation temperature, indicating at what temperature the INP are effective. The vertical axis shows the number of INPs per liter of air. The gray plot represents the blank results for the filter alone, while the green plot represents the results obtained from the samples. From this figure, we can see that, for example, INPs that are effective at -20 degrees occur at a concentration of 0.1 per liter, and those that are active at -30 degrees are present at a concentration of 10 per liters. Then I would like you to see a video of the actual measurement processes, and I'm not sure it works well. Okay, sorry. Thank you. Okay, this shows a freezing test of milky water. And the thermometer in the lower left currently reads -33.5 degrees. You can see that most of the droplets freeze around -34 degrees. And next, then the all droplets frozen at the -34.5 degrees. Next, we have the result from the test where mineral particles are suspended in the same milky water. If you look at the thermometer, it is currently around -23 degrees. And you can see that droplets are already freezing, and by the time it reaches -25 degrees, almost all of the droplets have frozen. This difference in freezing temperature is how we measure INPs. Okay. Now I will present the observation results of the INPs. These results are obtained in 2021. Sampling was conducted in distinct period from 10 a.m. to 6 p.m. and from 8 p.m. to 4 a.m. the following morning, clearly separating the day and night. The ice nucleating particle concentrations were plotted with red for daytime and blue for nighttime, showing a clear trend of higher concentration during the day. During the day, one phenomenon occurring on the mountain is very wind that arises from the warming of the mountain slopes, blowing from the base to the summit. Previous research had suggested that valley winds may transport mineral particles from the Mount Fuji to the summit. Recalling the type of particle that act as INPs, mineral particles are the primary candidate. Therefore, this is a slide. So recalling the type of particles that act as INPs, mineral particles are the primary candidates. Therefore, one hypothesis is that surface minerals of Mount Fuji are transported to the summit during the day by valley wind and function as INPs. To verify this, we collected surface mineral samples along the hiking trail to confirm their ability to act as INPs. As shown in the picture, we collected 3 types of stones commonly found on the Mount Fuji, crushed them finely, and selected particles smaller than 1 micrometer to investigate their ability to act as INPs. On the right is a figure evaluating the ice nucleating ability to act as INPs. On the right is a figure evaluating the ice nucleating ability of various mineral particles reported in previous studies worldwide. The horizontal axis represents the temperature, while the vertical axis indicates a measure of strength of INPs. In other words, the higher the points plotted on this graph, the stronger their ability to function as INPs. When we plotted the result of the minerals from Mount Fuji on this graph, they appeared as shown here, confirming that the minerals from Mount Fuji are highly effective as INPs. Using the result of the measured mineral particles from Mount Fuji, we calculated the concentration of mineral-derived INPs in the atmosphere, assuming that there were 0.1 micrograms, 0.1 microgram, and 1.0 microgram of mineral particles per cubic meter of air. They are represented by the black lines. It became clear that if approximately 1.0 microgram of mineral particle exists per cubic meter of air, it can generally reproduce the observed concentration of INPs in the atmosphere. It is generally said that there are about 10 micrograms of minerals per cubic meter of air at ground level, so the concentration of 1.0 microgram of minerals in the atmosphere is within a plausible range. From this, we confirmed that the mineral particles from Mount Fuji contribute to the INPs. However, relatively high activation temperature INPs have been observed that cannot be explained by mineral particles alone, as shown as a circle within the circle. What could this be? Among the particles that act as INPs, it is said that biologically derived INPs primarily originate from proteins, and it is known that they disappear when subjected to heat treatment. Applying this property, we conducted a screening test for biologically derived INPs using heat treatment. As a result, the proportion that could not be explained by minerals completely disappeared with heat treatment. This indicates that the missing portion was contributed by biologically derived INPs. Starting in 2023, we also decided to observe bioaerosol at the summit of Mount Fuji. We collected airborne particles in the mountaintop atmosphere using a dry cyclone sampler called Coriolis Compact. This sampler captures particle size between 0.5 and 10 micrometers by colliding them with a specialized cup. The suction flow rate is 60 liters per minute, and we conducted daily sampling for 14 days from 10:30 a.m. to 2:30 p.m. The analysis workflow for the collected sample is shown here. It's very complicated. Since we do not have access to next generation sequencer, we outsourced the entire process from DNA extraction to sequence analysis to a specialized company called Fastmark Corporation. In this study, we focused on bacteria among the bioaerosols and analyzed V4 region of the 16S ribosomal RNA gene. Then this slide shows the bacterium phylum composition obtained from our observation, along with the change in meteorological conditions. The bacterial community was mainly composed of Proteobacteria, Firmicutes, and Actinobacteria, which are commonly reported as airborne bacteria. For safety reasons, we avoided sampling during severe weather conditions. As a result, the temperature and relative humidity exhibit typical inverse trends seen on a clear day, and atmospheric pressure remains stable. However, on July 24th, we encountered bad weather, preventing sample correction, which is reflected as a blank in the figure. Next, we performed cluster analysis on the bacterial community at the genus level, as shown in this figure. The bacterial communities were divided into 4 major clusters. When we color-coded the meteorological data according to these clusters, we observed clear shift in the bacterial community corresponding to change in weather conditions. This suggests that the composition of bacterial communities was influenced by the air mass changes. These results confirm that our sampling effectively captured airborne bacterial communities and that the analysis was conducted accurately. The variation in INP concentration during the observation period is shown in this figure. For clarity, we have extracted and displayed the INP concentration at activation temperature of -10, -15, -20, -25, and -30 degrees. INPs active at -10 degrees, which are likely influenced by bioaerosols, were observed on July 27th, July 28th, and July 30th. This figure shows the INP spectra for the 3 days in question. The result after heat treatment used to confirm the presence of biological INPs are plotted in gray. On all 3 days, the INP active at higher temperature were found to disappear after heat treatment, suggesting the involvement of biological INPs. When we extracted biological genera that commonly increased or appeared during this period, 3 types were identified. 2 of these genera were associated with the surface of Mount Fuji, implying that biological particles originating from the mountain surface contribute to INPs. However, rather than suggesting that these bacteria themselves function directly as INP, it is more reasonable to interpret them as indicator of surface sediment being transported to the summit. I believe there are still various other methods to explore. However, since the data analysis is still in its early stage, I would like to continue collecting data while consulting with the experts participating here today. Lastly, I'd like to touch on how my research on ice nucleating particles relate to the theme of this seminar, micro-nanoplastics. Recently, a fascinating study was published showing that microplastics exhibit ice nucleating activity comparable to volcanic ash and fungal spores. Additionally, a slightly earlier study demonstrated that particles acting as INP tended to trigger precipitation, naturally returning to the surface with rainfall. Considering the seminar's topic on the circulation of plastics between land and the sea, the role of micro and nanoplastics as INPs seems to be a key factor in this cycle. And this finding comes from the research results of my collaborator, Professor Okuchi, who has detected microplastics in cloud water collected at the summit of Mount Fuji. Mountains where clouds and rain frequently form, clouds serve as hotspots for the material cycle between land and sea. In the near future, if we can conduct joint research between Mount Fuji and the Andes, it might significantly advance the theme of this seminar. The summary of today's presentation is shown on this slide. Thank you very much for your attention.
Le damos las gracias nuevamente al doctor Kotaro por su excelente y muy inspiradora, ¿cierto?, presentación. Es muy interesante lo que ha mostrado, justamente parte de ello también voy a mostrar yo en
Part of it,
propio
I will
seminario.
show it in my own seminar regarding the interaction between microplastics and clouds and formation, obviously, of these ice condensation clusters and water condensation that allow the formation of clouds and provoking changes in the hydrological cycles. Thank you. Gracias por su maravillosa presentación y su trabajo excelente en el Monte Fuji. Y seguramente podemos trabajar en conjunto en el siguiente tema en los Andes.
¿Ya apagaste?
Va a ser la hora, ¿eh?
Queda un chino, 20 minutos y se acabaron los chinos.
Que la va a coordinar, ¿cierto? Nuestro colega, el doctor Fumito María.
Fumito.
Okay, thank you, Francisco, for your kind introduction.
Por la presentación. Antes de pasar a las preguntas y la sesión de discusión, me gustaría agradecer al comité organizador por esto.
Really appreciate all the speakers from here and Japan. And in my opinion, this kind of seminar is not so popular. I think that as a speaker's contents, many of research is now ongoing and just before starting, and it means we need to more and more research, and especially from young researchers. And also, microplastic is, as you know, this is a worldwide problem. It means collaboration with many other countries, including Chile and Japan, is necessary. So I don't know, this kind of research has a very popular international consortium, but of course now microplastic is very popular, becoming popular. In addition to microplastic, some researchers now, for example, in the case of last speaker talked, in the final part, there is microplastic in the air. But one paper, recent paper in Science says, in addition to microplastic, we can find many nanoplastics in the air also. So, and also in addition to that, so maybe many of you know about microplastic, how to be affect to human health and also animal and fish health. But in the paper says, even in addition to our health problem, the plastic can affect to our climate itself, because there are now not so many papers exist, but abundant of nanoplastics are found in the air also. So it means plastic can absorb the sunlight. It means cause some changes in our climate. So two of our speakers talked about the bioaerosol. Bioaerosol is itself not so popular and not so many people can do because, as you know, many of microbiologists depend on the culture-based methods to analyze the microbe in the environment. But most of you now know many microbes in the air cannot be cultivated by our current culture techniques. So it means we need to analyze the microbes in the air must be used in culture independent methods. So it means, for example, in the case of speaker, Dr. Sof just showed real-time monitoring of bioaerosol using laser-based methods. So it means laser-based method is now still developing. So it means we cannot analyze the bioaerosols not so precisely now. So in the case of a device called BioTrack, use a laser and the system, we monitor the bioaerosols using riboflavin or tryptophan and NAD as a biological marker, chemical marker, to understand the particle is microorganisms. But as you know, in the case of air, in addition to bacteria or fungi or pollen, we can find many viruses in addition. But as you know, maybe in the case of seawater or lake water or other environment, if we use transmission electron microscope, how much number of viruses in the sample? Usually, in the marine environment, more than 10 or 100 times more abundant than bacteria. So it means viruses are most abundant biological entity in the natural environment. But no one still cannot count how many viruses are in the air. So it means we still have a lot of things which we cannot see so far. So it means now we recognize nanoplastics is in the air, and some, as you know, some and many of plastic recently is degraded by microbes. But no one knows how much nanoplastic in the air, and also how many microbes in the air, and how a microbe and bacteria or viruses are interact each other. So usually in the air, maybe you remember that in the case of COVID condition, some researcher says if we go out in a sunny day, we cannot be infected by COVID because COVID is very weak to sunlight, UV light, for example. But epidemiological study says if the place is highly contaminated, for example, winter season in Osorno is highly contaminated in the air. So there are so many soot by combustion of wood. So if there is a soot in the air, the SARS-CoV viruses can attach to soot and they can survive much more than expected. So it means in addition to such environmental problem, we need to consider the air condition to understand how microbes can survive in the air. So it means this time we're focusing on plastic and nanoplastic and some microbe related to, maybe related to microplastic, but still we don't understand many things so far. That is our key topic or key sentence. What we want to tell you from our Japanese side researchers. So I really hope to listen to Chilean side researchers talk in the afternoon and tomorrow in the morning, and then we hope we can conclude something. We can summarize what we need to do here. So we, as I said, there are so many topics. So it means we must try to prioritize. We need to make a list, and then we need to start what we should do firstly and secondly, thirdly. Such kind of approach is necessary. Then here we have a lot of different researchers from internationally and transdisciplinary. So now we can, as you know, many people understand that transdisciplinary approach is necessary. This time there are so many researchers from microbiology and meteorology, but this approach is very nice, and maybe we can invite other field researchers also. But firstly, we need to make some specific goal, and then we can invite more researchers to improve our science and try to solve this worldwide issue. That is my talk.
Questions?
Just summarized.
Ya. ¿No hay un micrófono inalámbrico dando vuelta? No. ¿Puedes preguntar? ¿Le da mucha vergüenza si viene aquí?
Muchas gracias por la organización del seminario y a todos los que han expuesto. En verdad, mi pregunta iba dirigida a cómo reducían la contaminación cruzada en el laboratorio y cómo evitaban la posible contaminación de esto que puede provenir de los reactivos al identificar microplásticos de muestras ambientales. Muchas gracias.
Translator.
Thank you very much to all to all the expositors and the organization of the seminar. My question is, how do you eliminate or reduce the cross-contamination in the lab for the identification of microplastics, especially from environmental samples? And how do you reduce this contamination that could be originated from the same reactors that we use from the identification of these microplastics in environmental samples? Thank you very much.
Very good question.
First of all, thank you for your question. Maybe the point is best. Very difficult question, but first of all, when we when sampling, maybe usually contaminated by process and growers. So maybe we wear the not polyester process like cotton wears. So different from environmental pollution contamination. Maybe we can understand that this is environmental pollution. This is contaminated from wares. This is an easy idea, I think.
Thank you very much.
First of all, thank you for your presentation. That was really nice. I think that I've learned a lot of the whole presentation of each of you. And my question is for Dr. Murata. So your research from Mount Fuji, basically at the summary said that the INPS are there by minerals, but also then you mentioned the bacteria of that and biogenic of the INPS. So my question is, INPS are related to bacteria or are related to the minerals of the composition of the mount? That's my question.
Thank you for your question. I think the mineral is the most abundant INPs in the atmosphere. So the INPs on the top of Mount Fuji is also mainly contributed by mineral particles. But more INPs active at higher temperature, minerals cannot work as INPs. Only biogenic INPs act as INPs. Biogenic one act as INPs. So the answer is both contribute to INPs in the atmosphere of Mount Fuji. And the composition of mineral is also important. Generally, K-rich feldspar is most efficient INPs among the minerals. So I should check the composition of minerals on the surface of Mount Fuji, and what minerals really contribute to INP.
Thank you for your answer. Following for this answer, I have another question about the efficiency of these different particles. You can measure with your method, with this copper plate, the efficiency for one particle to differentiate from another biogenic aerosol, or you cannot measure the efficiency. So, in terms of what is the conversion from the different particles to this EMP, closed particle. You understand the question? Because you say that both have the impact or have possibility to transform in this ice condensation nuclei. But the question is, what is the efficiency from this transformation of this particle? Is more efficiency the biogenic aerosol, or is more efficiency the mineral dust efficiency? What's more important?
Okay. In the atmosphere, if the particles act as INP at higher temperature, they easily transform liquid to ice. So INPs active at higher temperature is more efficient than INPs active at colder temperature. So if in terms of the activation temperature, the biogenic is the most efficient INPs.
¿Más preguntas? ¿Más cuestiones? Carla.
Yeah, thank you very much for all your presentation, very interesting. I have one question for you, Isoe. It was about, I was very impressed by the recycling methods that you mentioned, and by dividing the plastic waste in comparison to the incineration waste. And my question was, from all the plastic waste that you collect, is all of it recycled, or does some of it also still go into incineration plants?
So the collected plastic waste, recycle as possible as they can. But unfortunately, some plastic dirty
microplastic still remains some liquid in the containers. These are not suitable for recyclers. These plastics are treated by incineration. So the plastic waste recycling ratio is higher than over 80%, but almost is a summer. So it's not a real recycle system. So we need to change from the insulation to the material of chemical recycles. So Japanese research and some private companies are trying to develop the technology, especially chemical recycles. And firstly, we need to reduce the plastic waste and recycles that are horizontal recycles, not the down cascade recycling. We should produce some upgrade recyclers. So it is still ongoing. Yes. And another point is the market for the recyclable plastic. The very expansion of the market is a very big challenge because the recyclable material is higher than the nature products. So we need to expand the market expand the market for the recycled materials.
I think over 80%, I think that's also quite a lot. So
Yes.
Yeah.
Thank you so much.
One question? No? One question more for you. Yes. It's about the microplastic measurement in the waste treatment management from Japan. Is this so measured? Yes, please.
It's a very important point. So we also want to try to measure the microplastic around waste treatment facilities. There are many hurdles to clear the permission of the private companies. So we don't have any data about how much of the plastics are emitted to the atmosphere around in the facility or landfill site. So it's challenge for the future research. And in Japan, about the landfill site, so Japanese landfill site is covered with the soil. So I think that the plastic not emitted to the atmosphere from the landfill site. Mostly the treatment facility or during the transportation trucks. Yes. So, but the point of the worldwide, there are many open dumping landfill sites in another country. This landfill site probably emitted many plastic material to the atmosphere on the open dumping landfill site. So we should focus on the landfill site.
I think this is a very important issue to consider in the future from waste management, because the treatment is very depending of the different type of waste, and obviously this different type of waste produce a different type of microplastic and size of microplastic, shape of microplastic, and that is very important to consider in the future. And also to measure with filters that you can analyze. So with the technology that show in the presentation, touching and what is the amount of plastic that you produce in your waste treatment. Very important. ¿Más preguntas? ¿No? Vamos a entregarle unos presentes entonces a nuestros expositores, así que podemos pasar al doctor Itochi a present for you.
Thank you.
Thank you very much for your presence here.
Thank you very much.
Don't bother about it. It's a present for you. Thank you very much for your presentation. You will. Thank you very much for your presentation and for coming here. Come on. And Dr. Fumito.
I don't have a presentation.
It's a pleasure for you also to coming here. Thank you very much. We can take a photo together. ¿Podemos tomar una foto todos juntos acá?